So we're going to just take a quick stroll through section 3.4. There's not a whole lot of material to it, but I wanted to point out a couple things. One thing is we're trying to talk about how graphs representing data can be deceiving. And one of the ways, most important ways, is when more than one dimension is used. So most times on a bar chart, the widths stay the same and then the length, the height changes. And so we can compare them pretty easily because the width are the same. We're just comparing the changes in height. But if your pictograph has both dimensions changing at the same time, well, now you're messing with the area. And so you can't as easily detect exactly what the change is. So for example, if this length is supposed to be decreased so that it's 41% as much as the other one, then that would be fine as long as this width stayed the same. But when they both change size, your area now is only 17% of the other one. So the idea is you are going to have to pick one, change the length or change the width. Don't change both because then you're changing the area. And that's a perceptual distortion. Another problem is scaling. If your scale in your y-axis doesn't start at 0, then the same data can look a lot more extreme. So when you shrink your scale to go from 30 to 60 instead of 0 to 100, you make all of these changes seem more dramatic. So always look at what the scale is. This is another example of how changing the dimensions, in this case 3 dimensions, so they change not only the length, but the length and the width and the height. Well, when you do that, changes that if this is 4 times as long as that, and this is 4 times as long as that, and this is 4 times as long as that, you've just changed it by 4 to the third, or 64 times. So every increase in a dimension has to get multiplied up, and it changes the way your eye sees it. This is a lot more than 4 times as big as that. If your scaling has exponential as opposed to linear, then you have to interpret your graph differently. So you always want to take a look at what your scale is. It should be, these should go up in a linear fashion, not an exponential, because what you're hiding is how this graph really is shaped. As the years go on, it's increasing at a faster rate. You don't see that here with the scale being not linear. Percentage change graphs. They're common, but they're hard to read. They're easy to interpret incorrectly. So if you're looking at actual dollars over the course of years, and you can compare the public and the private yourself, that's a little bit easier to handle than these being percentage change from previous academic year. So you can't go up and say, okay, this is my value. You have to perceive that as a percentage change from the previous value. And so it takes a little bit more finesse to understand what that data is telling you. Pictographs that have a lot of artwork that is unnecessary can distract you from what you're looking at. So these people here are not helping at all in us understanding this data. Looking at 3 dimensions is always an issue. You want to make sure that only one of your dimensions changed. But then also looking at the years, they're not increasing in a linear fashion. They're not the same distance apart. And so that makes this difficult to interpret as well, because we sort of assume that would be the case. So whenever you look at a pictograph, you want to make sure that there's not something in there that might be trying to mislead you in how to interpret the data. So that is the end of the section 3.4. As I said, there's not a whole lot of information. Make sure you fill in your note sheet, and we will pick up with the next section next time.